Thank you, Chairman, and thank you for inviting me to this very nice conference. I'm going to talk about the perfect flat band induced by strong spin-orbit coupling. So the collaborator is my student, Hiroki Nakai, who has just entered the master course this spring. So we start from a brief introduction about spin-orbit coupling and the flat bands. So I think people all know that the spin-orbit coupling has been serving as an important source of physics for the last 20 years, and it includes the Lasher-Butterfield effects and spin-dependent transports, and also many different types of topological phases of matter, and even a spin decade, which is also a topological order. But now I would like to add one more perfect flat band to this list, which I think to be quite exotic. So this talk is related to the actual material cesium tungsten 207, which is a pyrochlore filled electronic system. So I'll go back to this on the latter half of this talk. But first, I'm going to show that the spin-orbit coupling will yield a perfect flat band in the first half of the talk. Okay, so flat bands. So people, I think, are familiar with the origins and how the details of the history of the flat band. So, oh, I'm sorry, I just probably, maybe I skipped one slide. Okay, but okay, so I will just briefly mention, I had one more slide previously, but I lost somewhere. I'm sorry. But anyway, this is one of the quite series of flat band works presented in 2011 by 3 successive PRO papers. And those papers aimed to realize a nearly flat band. I mean, they wanted to have a flat band with a topological non-zero Charn number. And actually, they succeeded in having a non-zero Charn number by, for example, in the first work, they introduced a spin-orbit coupling term to the, the kagome lattice, and I'm sorry. And the second one, they introduced a flux, like we quite often know for the Hotta model. And the third one, they wanted to make a more realistic realization of this kind of topological Charn number by controlling the tight binding model in a realistic orbital geometries. Okay, but in all cases, empirically, they turned out that if they want to have a non-zero Charn number, the band cannot become perfectly flat. So they're going to gain a very small but finite dispersion. Actually, when these kinds of spin-orbit coupling, for example, introduced, the kagome material, kagome flat band, for example, will lift the band touching with other bands coming from the lower part. And then there's going to be a gap opening, and that is the reason why they could just gain a finite Charn number. And that is actually realized in this material, in this NatureCom paper. Okay, so their aim was originally supposed to realize a high temperature fractional quantum Hall states without a magnetic field. But so adding the topological nature will lose the perfectness of the flat band, which is proven later on in 2014 by this paper mathematically. So let's go back. This was the original slide. We have several classes of flat bands. One is the line-graph family, which is already known, very famous ones. And the second one is the one which I have previously introduced, the topological nearly flat bands. Hatsuga Sensei will also probably tell us about this probably in the later half of the conferences. Okay, and there's also a twisted graphene, which is empirically known to have a flat band like this. And this kind of flat band is in, like, many people have been interested in this flat band because they might be related to the superconductivity realized in this twisted graphene. Okay, there are several more recent papers, but I don't go into this in detail. Okay, so let us summarize what is already known for the flat bands. So the flat bands will occur in a series of Brine graphs, or when the fluxes are introduced or the fluctuations are introduced. And if the non-zero Charn number is introduced, for example, by the spin-orbit coupling, unfortunately, the flat band will lose its flatness and become nearly flat. So it's practically fine, but theoretically it's not perfect. Okay, so the other two ingredients are something which is already well known for the for the flat bands. One is that the flat band wave functions can be derived by hand by constructing some sort of a loop one body wave function in space, and they are localized in space so that they cannot contribute to the finite bandwidth. And this is because of the so-called destructive interference effect, which I'm going to go back to it on later slides. Okay, so once we have a flat band, and if we introduce a finite but infinitesimally small Coulomb interaction, it is known that if the flat band is less than half filled, we're going to have a ferromagnetism. This is like an outcome of the first paper by Nielke and Tasaki. It's work in 1991, I guess. Okay, so reminding of all these issues, what we want to do is to find the flat band induced by spin-orbit coupling. So far, we have discussed that the spin-orbit coupling will lose the perfect flatness of the band. But now in our case, the spin-orbit coupling will assist the flatness of the band, which I'm going to show you in this Hamiltonian. So this is the Hamiltonian. This is a kinetic part of the Hamiltonian. It includes the usual hopping T and this spin-orbit coupling induced hopping lambda, which is spin dependent. So the spins when hopping from one side to another is going to change its direction depending on this axis nu and this coupling lambda. I'll go back to this later. Okay, so I'm going to think about the pyrochlore lattice, which is one of the famous line-graph line-graph family lattices. And we consider an extended unit cell including 16 sites, and we are going to put 8 electrons onto this system. So it's going to be quarter filling. We have 2 electrons per each tetrahedron. Now, we first straightforwardly diagonalize this Hamiltonian, which is noninteracting. Now, we first come to the energy band without spin-orbit coupling induced lambda. Then we find a very familiar flat band at the top of the energy band. And since this, this unit cell includes 16 sites, we have, including the spin degrees reading, 32 sites, but half of these bands become flat at the top. Now let us introduce lambda plus and minus. And then we find that because of the spin-orbit coupling, the flat band becomes not perfectly flat, but nearly flat. And then we evolve this lambda, and then the bandwidth will become larger. And in this value, lambda over t minus 0.5, the band is completely symmetric, so it can be upside down. Now let's further increase lambda, larger and larger. And then the plus and minus will become different in their configurations of bands. And now finally, if we go to -2, we finally get a flat band on the bottom, which is again like 16-fold degenerate. Namely, half of the energy bands are flat and degenerate at the bottom. And you can make this flat band upside down to recover the first energy band at lambda equals 0 by shrinking the bandwidth to 1/3. Okay, so this kind of beautiful kind of symmetric behavior does not happen by accident. So there's an underlying reason, a theory that should explain this kind of phenomenon. So let's go in more detail to see what's the nature of this Hamiltonian. So this Hamiltonian includes T and lambda. So if we put these two terms together and form this kind of 2x2 matrix, this is going to be a non-abelian SU2 gauge field. This non-abelian SU2 gauge field can be described by the exponentials of -I times 2 over theta over 2 times nu dot sigma. And this is nothing but the rotation of spins by theta, angle theta, about the axis nu, which is a vector. Now, just so that if you have an electron on the J site, and if we want to hop this electron to the I site, the spins pointing somewhere in the J site will be rotated by theta in hopping about this new axis. So this is the role of the spin-orbit coupling, okay? And Now, so then how can, and this theta can be described by the combinations of lambda over t. Okay, so then this, to understand much more about how these spinor coupling work, we first go back and review the original line graph theory. I think people know about that quite much, but this line graph theory, we just review on a pyrochlore lattice. We have a pyrochlore lattice, and now, oh, sorry. We now create another series of lattice by putting another red site on the center of each tetrahedra. And this is going to form a diamond lattice by itself, this red one. So the diamond in the pyrochlore is not mathematically exact, but it's gonna become a dual lattice with each other. And now, if you erase the pyrochlore bond, and then we can get a bipartite lattice like this. And then let us define or introduce a so-called incidence matrix, which will transfer the pyrochlore to the diamond, or the diamond to the pyrochlore. So we have for each row a pyrochlore site and each column a diamond site. So the entry, for example, entry 1C1 is 1 because we have a finite bond connecting site 1 and C1 in this blue line. And by constructing this kind of incident matrix by putting ones to all entries that have the connections between the pyrochlore and the diamond side, we're going to end up with this kind of matrix with n by nd. Okay, so the dimensions of rows and columns are different because the numbers of the pyrochlore site and the diamond site are different. Now, once we get this TOD, we can reconstruct a pyrochlore tight binding Hamiltonian, the matrix representations of the helping Hamiltonian of the pyrochlore lattice, by multiplying this TOD with TDO, meaning that we will trace out the degrees of diamond lattices by multiplying it. And this will indicate that the pyrochlore electrons will hop to the diamond lattice and go back to the pyrochlore site again. Now we have an extra diagonal term, 2 times Ti, which is because we once go to the diamond site and then go back, we have a unit back, we have a contribution of a diagonal term, and we have for each pyrochlore site 2 different neighbors of diamond sites, so that it's going to give 2 for each diagonal element. Now, once we get this form by introducing the incidence matrix, we can automatically see that the flat band exists, because this TDO is not a regular, not square matrix, so that they definitely have a finite numbers of dimensions of kernels that will give zeros when operating to some vectors. So this vector is going to form a kernel of finite dimension. And once this kernel is obtained, this is also going to serve as a eigenstate of the pyrochlore Hamiltonian with the energy 2 times T, which is non-dispersive, and this is going to be the flat band. And because this is not a regular square matrix, the numbers of rows and columns differ, so that they're going to have 8 flat bands in all for this kind of construction. Now let us apply this line graph theory again to our theory. Okay. Now, remind that in our theory, we had an SU2 gauge field, so that hopping is going to just transform the spin directions to the others. Now, so this means that the dimensions of matrix should be doubled because we need to include the spin degree freedom explicitly. And we need to define an incident matrix that will also fulfill the same relations as we saw before, but with different dimensions of TDO. And now we found that by preparing this incident matrix, which has elements not one, but some sort of a spin rotation element, we can recover the similar types of relationships with the original spinorbit included pyrochlore lattice hopping with this new incident matrix with a doubled unit cell, and the spin rotation included elements. So then once we get this form, we can immediately see that the kernel of this new incidence matrix will serve as a flat band wave function of the spinorbit included pyrochlore lattice, and that will give us 16 different flat bands in our case. I'll show you later on how this kind of thing will work, but this holds when and only when lambda over t is -2. So this incident matrix will serve as such that if the electrons will hop from site 1 to C1, it's going to be rotated by pi. And then from C1 to C2, again rotated by pi. And this axis of rotation is like determined uniquely by the symmetry argument that they should only point in this direction, these two directions. Now, why we only have this kind of constructions at a single lambda over t equals -2 can be explained a bit more in a cartoon picture. So let us start from this this site pointing, the spin is pointing in this direction, and then they just rotate by pi, and then they're going to become this kind of angle. And this theta prime is the angle which is determined by the geometry of the lattice as such that is going to be arc cosine cos square root of 2/3. Now, again, it hops, and then it's going to also be rotated by 4 pi, 4 theta prime. So if you operate twice this pi rotation hopping, it's going to change the spin angle by 4 times theta prime. So if this 4 times theta prime equals theta in the original Hamiltonian, it's going to give us the construction that is going to fulfill the previously showed relationships between the original pyrochlore lattice and the incident matrix, and that will give this kind of relation. A more hand-weaving way to derive this theta is to see that these two vectors just mediating C1 and C1 and C1 and 2 sides is going to have angle of theta over 2. And if this angle will be fulfilled by lambda over 2, lambda over t, is going to give a perfect flat band. Now, so the similar thing can be discussed for the kagome lattice with a similar Hamiltonian, which is also including a spinorbit coupling term. And in this case, if you just change lambda over t to 0 to square root of 3, it again is going to become upside down, and the top flat band will become a bottom flat band. So the theory is quite general as far as we can get a proper spinorbit coupling Hamiltonian. Now, let's see what's going to come out as a physics from the spinorbit flat band. So the motivation of this work was to clarify the trimerized charge order state of the 5D material cesium tungsten 206. This material has a pyrochlore band structure, and it undergoes a metal interactive transition at 200 Kelvin, around 200 Kelvin, to the low temperature phase, which has a trimerized charge ordered phase. And in this charge ordered phase, it's quite tricky that 1/4 of each of the tetrahedra become completely empty. And this kind of very perfect exclusions of the electron occupancy cannot be obtained by the strong correlation. So there's some underlying physics behind, and I would say this is going to come from the perfect flat band. Now, why this material has that kind of Hamiltonian can be explained by the crystal field analysis. This is a 5D electron where we have 1 electron on the T2G orbital. And because this tungsten ion is surrounded by 6 oxygen ions, they're going to feel a crystal field of a trigonal symmetry. So the trigonal symmetry will split the T2G orbital into 2 parts. And finally, if you introduce a large spinorbit coupling originating from the tungsten ion, it's going to further split the orbitals into 3 doublets. And this resembles the situation of the iridates, because iridates, they also have similar splitting. In our case, we have a single occupancy on the bottom of the band. Now, because these iridate E3 and RE2 share the same constituents of the E1G and E2 pi, we can immediately see that they're going to share the same Hamiltonian, and that is the Hamiltonian that we discussed previously, including a spin-orbit coupling induced hopping term. Why this hopping comes out is that this doublet, which we consider to be the pseudo upspin and pseudo downspin levels of a simple orbital, is that this pseudo upspin and pseudo downspin includes the true upspin and downspin levels combined with the orbital momentum, so that if you want to hop A1G upspin to the nearby EG upspin level, it's going to flip the spin from up to down and down to up like this. And that will induce a spin-orbit coupling induced hopping. Now we want to include an on-site Coulomb interaction in the nearest neighbor Coulomb interaction to this material. And I'm not going to go into details, but this Hamiltonian also shares the same physics as the iridate Hamiltonian. But anyway, we are going to focus on the quarter-field case. And now this is a mean field phase diagram. Now this phase diagram has been just drawn on a plane of lambda over lambda and v by fixed u. And you can see that there is a very large region where the 3 in 1 out phase is going to be very stable down to very small degree. So what is this 3 in 1 out phase? Is that I borrowed the notations of the spin pyrochlore spin systems, in that in means occupied state and out means an unoccupied state. So in our case, 3 in 1 out means that 3 sites are occupied and 1 site is empty. 2 in 2 out means that 2 sites are occupied and 2 sites are empty. And uniform metals, they have for all these 4 sites on the pyrochlore lattice to be uniform in space. So the mean field result indicates that this 3 in 1 out phase is very, very stable around the flat band parameter. So let's see why it's going to happen. So in terms of the band structural energies, I mean the band kinetic energy, if you, for example, compare the energy band of the pyrochlore and the hyperkagome at this magic number of lambda over t equals -2, we see that the hyperkagome lattice, which has a trimerized charge order state, is going to have also a perfect flat band at the same location as the pyrochlore lattice. So it means that if you calculate the band energy, at this point, these 2 energy bands will become equivalent in energy, so that usually the pyrochlore wins in the usual parameters, but in this flat band case, the hyperkagome and the pyrochlore lattice will become equivalent in terms of the band structure energy gain. Now then, if you want to consider the interaction term, we need to go a bit back to the usual flat band theory. The flat band theory, we have already known that one can obtain a flat band one body wave function in the shape of the loop. So this is a case of the kagome. We have loop 6 and loop 10, loop 40, I'm sorry, larger loops. But how these loops function is that if you place sign of one body with one function operate, this will be 1 plus minus plus minus plus minus. If the electrons want to hop to the nearby vertices, these 2 hoppings will kill each other because of the difference between the phases and difference with the same weight. So this is called the destructive interference effect, and this will work for all different loops constructed on these lattices. Okay, then if you go to the flat band many body wave function, if you just make a product state of this one body wave function, it will serve as a many body wave function. And it is already known that including the correlation to this kind of a product wave function, you can find a flat band ferro by Mizuki-Tasaki theory, because it's better to polarize the spins to avoid W occupancy automatically by the Pauli's principle, other than just making up and down together on the same site. So it will just automatically select the polarized configurations of spins. based on this flat band construction. So in our case, the similar thing will happen. We can construct similar loop wave functions consisting of 10 sites on the hyperkagome like trimerized charge order state. So by so this loop 10 has a particular feature in the sense that they need to have a particular type of spinor radiation, because if they want to have a destructive interference, as we saw in the previous slide, we need to just control the spinor radiation on 4 different sites to be such that if they come to the diamond side, they kill each other after rotating. So the spinor radiations will be completely locked. But once we allow this kind of configuration, we can just contrast this loop 10, one body wave function, and then successively we can get a many body wave function out of this loop 10 and make a 3-in-1-out state. And this 3-in-1-out state will automatically have u equals 0 and v equals smaller than the mean field value, so that it means that if we could properly get a many body wave function based on the flat band, it will gain also the interaction energy. So this is almost the final one. So this is the Hamiltonian, including U and B. So that previously we were thinking that 3-in-1-out was not favorable, but now if you include the constituent of the perfect flat band, we can see that 3-in-1-out will win both the uniform metal and the 2-in-2-out one. And so we can get trimerized charge ordering benefited by the strong spin orbit coupling and by U and V. So this is basically the summary of my talk. We found a spin orbit coupling can yield a perfect flat band, and similarly to the Miyake-Tasaki ferromagnetism, it will favor trimerized charge ordering by the very small interaction term. So thank you very much for your attention.
Okay, thank you very much, Chisa Hotta, for this excellent talk. Thank you. We have enough time for questions. It looks like Om Jung already prepared, so unmuted.
Yeah, so, okay, let me start. So yeah, it's very interesting talk. So I have 2 questions. So one is actually, I don't understand the nature of the 3-in-1-out state. What do you mean by 2/3 of the charge is localized at each side? What do you mean?
You mean the configuration of 3-in-1-out?
Yeah. So we have
so we
2/3 of charge at
Yes. So originally we had I'm sorry. Okay. So originally we had this kind of pyrochlore lattice, which is a corner share tetrahedron, right? So we have if we just focus on each of these tetrahedron, which is corner shared. And that 3-in-1-out means that one of these tetrahedron sites is fully empty, and other 3 is filled. So this is the meaning of what we call 3-in-1-out.
If the total number of electrons is 2.
Yes, 2. So we have 2 electrons per two electrons per tetrahedron. So we can assign it to different in a different ratio and see which is going to be energetically favorable.
Okay, thank you. So the second question is actually, you explained the structure of the spinor coupling very carefully using this orbital structure. But is the spinor coupling term different from the usual KML term? Is it different from that?
I'm sorry, your sound is sometimes like I could not hear you.
Yeah, you explained spinor coupling in terms of the orbital splitting at the constant side, right?
Yes, this one.
Yeah. So if you look at the form of the spinor coupling, is it different from the usual KML type spinor coupling, or does it have the same form?
This is completely the same form as the usual spin coupling of the iridates. So the iridate also has this symmetrically the same type of crystal field orbitals of 3 doublets, but the filling is different. So iridates, they have like 1, 2, 3, 4, maybe 1, 2, 3, 4, 5, 6. All these E1 and E2 are filled, and E3 have 1 electrons. So they only need to focus on this E3 level. Our case, we only have 1 electron because we are focusing on the tungsten ion. Iridates, they have, so, but in this case, it looks different because the effective momentum is different, right? This is what happened to third, but because the constituents are the same. So E3 is consisting of Eg pi and M1G, and E2 is also consisting of the same constituent with only the coefficients different. So they share the same Hamiltonian, just the parameter values are different.
Okay. Thank you very much.
Yes.
Okay, thank you.
Yes.
Question?
Yes, please.
Hi, Chisa. Yeah, that was beautiful. Thank you. So I'm naturally curious about your many-body wave function. So you said you're going to use this 10-loop state, and you formed this many-body wave function. So could you explain a little bit more about this? So
this is quite a new finding. So it's quite tricky. So so in the original pyrochlore unit cell, extended unit cell, we have 16 sites, and we have 4 different kagome layers on a pyrochlore lattice. And each kagome layer consists of 6 loop 6 of hexagon loop, 4 hexagon loops for each kagome layer. So
so this thing contains usual hexagonal loop, but you're not using that. And
this is because we need a depletion. We want to construct a wave function without these fourth site. We want to deplete it. So we don't want this guy to join this wave function. So in that case, the choice of the hexagons are limited in the case that, these 10 loops are the combinations of 2 hexagons by depleting one site, right? And then we can just construct 10 loop 10, and we can construct 4 independent loop 10s in the unit tetrahedron. So that will compensate for all the flat bands. And if we just multiply it, we can get a perfect 3-in-1 out configuration. And if you just like, it's quite complicated.
Anyway, so you're using all the possible, you're using every loop 10. So there's no choice.
We have like arbitrary choices. Like we have for each depletion site, we have 3 choices of choosing 2 10 loops, but they are not independent of each other. So anyway, we only have 2 independent loops for each depletion site. It's a bit tricky.
So
all of them,
And is this something rigorous, mathematically rigorous, or?
I think so. We have tested whether our assumptions are right by just testing all these operators like eta, and then we found that it's gonna work actually.
Okay, thank you.
It's quite complicated. I'm sorry. Yes, I skipped this.
Okay. Further questions? Maybe I can ask one. You mentioned also the term spinor-line-graph theory. Now I thought I do know a bit. I learned a bit about the line graph theory of constructing flat bands. Are you referring to that, and are you decorating it with the term spinor, and therefore there is a new line graph construction of flat bands in systems in the systems you considered, or what is this term meaning?
Okay, so why I include the spindle is that in the usual line graph theory, this one, we don't consider explicitly the spin degrees of freedom.
Yeah, I understand that, but okay, thanks.
So the construction is completely the same. The construction, the shape of, for example, this shape, the original flat band, original tight bind model can be explained like in the form of a diagonal term minus the product of the incident matrices. And this is the same as the usual construction.
Okay.
But just that the dimensions of the two matrix and the elements of the incident matrix will be a bit complicated. It will be doubled. And the elements are not 1, but spin rotation form. It's like a complex number. So
Okay.
so this is the formally is almost the same, but we only need to include the spin orbit coupled hopping to this infinite matrix, and that will give the same flat band construction. Once we could find this kind of infinite matrix that will fulfill this equation, we immediately get a flat band. So the important thing is to find this TOD for any of the Hamiltonian.
Okay. Yeah, thank you. And yeah, at the very end, you mentioned order by disorder. What did you mean by that?
Oh, yes, I did not properly explain it. I'm sorry. So the reason why is that, okay, I need to probably go back to this point. So I was in a hurry. Okay, so here in our slide, we had a degeneracy here, right? The pyrochlore and the hyperkagome has a kind of a degeneracy. I'm sorry. So this degeneracy will be lifted by the finite U and V. So uniform metal and the hyperkagome, or I would say that 3-1 state has the same band energy. So if they don't have a Coulomb interaction, they are completely degenerate in their shape. But if they introduce this Coulomb interaction, it's going to be kind of an order state. This is very similar to the order by disorder physics of the frustration physics.
I see.
It's not. It might not be that much clear. I'm sorry. Yes.
Oh, no, that was very clear. Thank you. Right. Further questions, important questions. We are almost at our time limits. If that's not the case, then let me thank Chisa Hotta and all the speakers of this first session. Thank you very much.